Hello, everyone. This is just really a test for a hangout I plan to do later. What I wanted to do, though, is read a terrific passage, Parasite Rex by Carl Zimmer. It says, Inside the bizarre world of nature's most dangerous creatures. It's a really good book. On the back, it says, Imagine a world where parasites control the minds of their hosts, sending them to their destruction. Imagine a world where parasites are masters of chemical warfare and camouflage, able to cloak themselves with their host's own molecules. Imagine a world where parasites steer the course of evolution, where the majority of species are parasites. Welcome to Earth. The part I want to read is a really interesting passage. It's in chapter 3 called The 30 Years' War. It describes what happens when an invader attacks our immune system. For those of you who are unfamiliar with this, I think you might find this interesting. The immune system attacks an intruder, bacteria crawling into a cut, for instance, in a succession of waves. Is a collection of molecules called complement. When complement molecules hit the surface of bacteria, they latch on and change their shape so they can snag other passing complement molecules. Gradually, the molecules build up on the surface. They assemble themselves into like drills that can open a hole in the bacteria's membranes. They also act like beacons, making the bacteria more visible to immune cells. Complement molecules also land on our own cells, but they do no harm. Our cells are coated with molecules that can clamp onto a complement molecule and cut it apart. Also arriving early at the cut are wandering immune cells, the most important of which are the macrophages. They have some crude ways of recognizing bacteria if they happen to bump into them, and they can suck the invaders into their cores and slowly digest them. At the same time, the macrophages also release signals that bring the rest of the immune system's attention to the site. Some of these signals make the infection swell up by loosening the neighboring blood vessel walls. That lets other immune cells and molecules flood into the tissue. The signaling molecules released by the macrophages also latch onto immune cells that happen to be floating by in nearby blood vessels. They lead the cells through the vessel wall into the infection, like a boy dragging his mother by the hand down a toy store aisle. Enough time, the immune system can organize a new wave of attack using much more sophisticated cells, B and T cells. Most of our cells come with a standard issue of receptors on their surface. One red blood cell looks pretty much like the rest. But when B and T cells form, they shuffle the genes that make the receptors on their surface. The cells use the altered genes to build new receptors with shapes not found in any other immune cell. This shuffling can produce hundreds of billions of different shapes, so that each new B or T cell is as distinct as a human face. Because they are so diverse, B and T cells can grab a huge range of molecules, including foreign molecules that trigger an immune response are called antigens. First, though, the cells have to get a proper introduction to the antigens. This job is accomplished by macrophages and other immune cells. As they engulf bacteria or their cast-off fragments, the immune cells cut them up into little pieces. They then bring these antigens to their surface, displaying them in a special cup, the major histocompatibility complex, or MHC for short. The immune cells travel into the lymph nodes. There they bump into T cells. If a T cell has the right kind of receptor, it can lock onto the antigens displayed by a macrophage. As soon as it recognizes the antigen, the T cells start multiplying quickly into a battalion of identical cells, all equipped with the same receptor. These T cells can take one of three forms, each of which kills the invaders in a different style. Sometimes they become killer T cells, which search the body for cells that have been infected by pathogens. They recognize infected cells, thanks again to MHC. Like macrophages, most cells in the human body can display antigens on MHC receptors of their own. If the killer T cell recognizes these signs of trouble, it commands an infected cell to commit suicide. The parasite within dies along with it. In other cases, activated T cells set out to coordinate other immune cells to do a better job of killing. These cells crawl their way to the macrophages that are struggling to fight the rising tide of bacteria. They lock onto the antigen displayed on the macrophage's MHC. That locking acts like a trigger, turning the macrophage into a more violent killer, spraying more poisons. At the same time, the inflammatory T cells can help make the cut swell far more than the macrophages can manage on their own. The inflammatory T cells also kill off tired old macrophages and spur the production of new cousins. They're a little like battle-hungry generals. They're good to have around in a war, but can't be allowed to get too out of control. Too much inflammation, too many poisons created by macrophages, and the immune system will start destroying the body itself. In the third form the T cells take, they help B cells make antibodies. B cells have the same diversity of surface molecules as T cells, so they also have the potential to snag onto billions of different kinds of antigens. After a B cell has latched onto a fragment, a helper T cell may come along and hook onto it at the same time. In these unions, the T cell can give the B cell signals to start making antibodies. Antibodies are a kind of free-floating version of a B cell receptor, also able to clasp onto an antigen from an invader. Once they're activated, B cells spew antibodies out in the body, and depending on the particular antibody, they can fight the infection in several ways. They can cluster around a toxin made by bacteria and neutralize it. They can help the complement molecules try to drill into the bacteria to make bigger holes. They can latch onto bacteria and foul up the chemistry they use to invade the body cells. They can tag bacteria to make them a clearer target for macrophages. As the majority of B and T cells go about eradicating the bacteria from the cut, a few set out the attack. These are known as memory cells. It is their job to preserve a record of the invader for many years after the infection. If the same kind of bacteria should get into the body again, the memory cells can switch back on and orchestrate a swift, overwhelming assault. These cells are the secret to vaccines. Even if immune cells are exposed only to an antigen, they can produce memory cells. Because a vaccine contains only a molecule and not a living organism, it doesn't make a person sick, but it can still prime the immune system to wipe out the pathogen if it ever meets up with it again. T cells, B cells, macrophages, complement molecules, antibodies, and all the other parts of the immune system form a tight net that perpetually sweeps our bodies clean. Every now and then, though, a parasite slips through and establishes itself. It isn't simply to some oversight, but to the parasite's ability to escape the immune system. Bacteria and viruses have their own tricks, but many of the most intriguing strategies are found among the classic parasites, the protozoa, flukes, tapeworms, and other eukaryotes. They can evade the immune system, distract it, wear it out, and even take control of it, confusing its signals into a weakened state, or if need be, a heightened one. One sign of the sophistication of these parasites is the fact that there is still no vaccine for them. While there are many vaccines for viruses and viruses. If Lancaster had known it wouldn't have given parasites a bad reputation they still haven't been able to shake. And that's the end. But I find that really interesting passage because it shows that our body is constantly at war with invaders. This is my test. I'll stop now and then I'll check it out to see how everything went. Thank you for those of you who bothered to listen.